So this is work that we've been pursuing for over a year now, into a long paper that should be posted pretty shortly. So this started when we were talking to Jean-Pierre Bourguignon about the epidemic in the spring last year, it was northern spring. And he pointed us at a FAPEST, and that will come at again in what follows. But it's absolutely clear that there's been a horrific cost of the reactions to COVID-19 and the disease itself. In its impact on the healthcare system. This is what's terrified politicians and policymakers the world over. So the Gompertz function, which I first heard of as a result of Jean-Pierre's tip to watch the FAPEST meeting, is it provides predictions that are accurate enough for planning. To manage the loads in their hospitals and intensive. The key to recognizing the transition to endemic disease and its seasonal cycles, and to predicting the course of further outbreaks. So let's just, especially as there might be some non-specialists on the call, the whole purpose of mathematical models is to allow us to see into the future. And the test of any mathematical model of phenomena in the real world is its predictive power. And Feynman's famous dictum, if it disagrees with experiment, or in our case, observation, it's wrong. So it turns out, and this took us a very long time, but there is a wealth of historic observational data and on epidemics going back to the 19th century.
Not very easy to find.
Not very easy to find. However, it exists. And that data shows that epidemics are described very well by a simple three-parameter phenomenological model, the Gompertz function. So that model accurately predicts the course of epidemic waves or cycles of endemic outbreaks, such as we began in 2020 with COVID-19. It's a data-driven approach to make forecasts of demands on healthcare resources that are accurate enough to plan for likely seasonal outbreaks in the future. So this was the seminar that Jean-Pierre recommended. So people had been very worried that the growth in cases was exponential. Something which is actually very hard to sustain in nature. And Michael Levitt, the Nobel laureate from Stanford, data very early on. And he observed from that data that rather than exponential growth, he was seeing a Gompertz function growth. I'll show you what a Gompertz function looks like in a moment if you haven't seen it before. But the big difference here is that in exponential growth, as we know, the doubling time is constant. That's what makes them so. But the Gompertz function the epidemic more and more as it progresses. So here's the Gompertz function. It's just a multiple of what's actually called the Gumbel distribution, a probability distribution. we'd never heard of a Gompertz function, but we know a very great deal about Gumbel distributions. And that will come into play as we go along. So here N is recording cases as you go along. And the other two parameters control the rate at which the cases grow, and B is related to the initial value of X. It turns out, in fact, that A and B are the constants of integration of a natural differential equation. Although in the literature, what you usually see, oddly enough, is people trying to explain how this equation arises in using first order, a one-parameter family of first-order differential equation. So these three parameters you can estimate directly from case data, and you get more and more convergence, if you like, although that's not exactly the right and fold. So just nonlinear regression will allow you to fit this model. Last year published a massive number of predictions for cases and deaths all over the world, cities, states, countries. There were, I think, 3,000 or 4,000 in the first release. Now, what we've shown is that this shouldn't have been a surprise that you could use this to get accurate predictions, because it's all every epidemic we've been able to get our hands on data for in the past, viral and bacterial. So here's the list. We found cholera from Denmark in 1853, but that required the help from the Danish public servants. Bubonic plague from Bombay in 1906, which was the subject of the Kermack and McKendrick's first paper introducing compartmental models. The Spanish flu, the famous epidemic. We have data in SARS-CoV-2, the original SARS-CoV epidemic in '09, Ebola in Sierra Leone in 2014, Zika in Colombian province of Antioquia in 2016, bubonic and pneumonic plagues in Madagascar 2017, influenza cases in Portugal 2017. So here's what they look like. This was in Aalborg, Denmark, 1853. It predated any knowledge of bacterial transmission, and also the famous pump handle incident in London a few years later that stopped a cholera epidemic there. John Snow, I think, was
just started and evolved and ended.
Yeah, so this is bang, bang, bang. And it was horrifically deadly. More than 50% of the cases resulted in deaths. This is the speed at which these things evolve is given by that A parameter, which is listed here. These are in order A, B, and N. And that's the biggest one that we've seen so far. So here's the Bombay plague. This is data that's only at roughly weekly intervals. It's actually been digitally digitized from the Kermack-McKendrick Royal Society paper. So it's probably the worst data we've got. You can see again the characteristic fit. Here's Prussia, the Spanish flu, which hit them just before the end of the First World War. And there you see a remarkable fit, as many of them are. And we constantly surprised by how strong the fits are. But there are reasons that we'll come back to for that. Here's the Spanish flu in San Francisco in 1918. SARS in Hong Kong, into Ebola in Mexico. Ebola situation reports from the World Health Organization in 2014-15. This is weekly data. Zika in Colombia, the bubonic plague in Madagascar, the pneumonic plague in Madagascar in the same year. And here's another spectacularly good fit. These are influenza cases in the Alentejo reporting district in Portugal in the 2017-18 flu season. This is data that the Portuguese National Health Service collects. And here from the CDC is weekly deaths from pneumonia and influenza combined. It's mostly influenza that kills these people, but they very, very closely follow the Gompertz function. And 2017-18 was the last really bad flu season in the Northern Hemisphere. So there's no doubt that this model describes the courses of all these epidemics very well. You can see that I mean, in lots of physics disciplines, you'd be looking for your Nobel Prize if you could produce fits like that to experimental data. The real question, though, is, does this do us any good? Or is it just a sort of after the fact, somehow, it gives a pretty description of what happened? So we need to know how well this works, and that means knowing whether, if we found the fit to the data up to time t, it allows us to predict cases for some t plus tau into the future with a reasonable degree of accuracy. Okay, so we have to we have to check that. That's error. So the absolute value of the percentage error between the actual observed and our data of 10%. The idea being that if you're an administrator and you know within 10% the loads on your system for a week, 2 weeks, or 3 or more weeks into the future, you should be able to cope, or you're in the wrong job. But this is an arbitrary cutoff. Now, it's very hard to. In other words, what we've done in the measurement is draw a band like the dotted band you see around the data here, but we've drawn it around each of the fits. They're glommed right onto the data up to the point where they appear difference. But you see that they don't give you extremely good predictions for a very long time. So here's what the error you see there goes off the chart, but it actually stays within 20% for almost 2 weeks, right? And after that, you're golden. Famously turned into an exercise in prediction competition for the epidemiological community after this year's outbreak, because they were unhappy with the accuracy they were getting. So we only have weekly data there. The first fit was done 4 weeks after the start, and we updated weekly after that. Accuracy, less than 20% error for 2 weeks. In subsequent fits, you got down to below one, but everything else did. So this is showing remarkably good predictive power. So in this 2020 COVID-19 outbreaks, the Gompertz function performed exactly as you should have expected given this historic record. One big difference is that this time, as well as cases and deaths, there's data on hospital and intensive care admissions from some countries and regions. So you can check that you can make and accurately predict the future using this simple model. So here are examples from locations where there was an enormous range of different public health policies. Let's see now, you always find the typos when you give the talk, right? So these are we found just last week, we found finally a data source for France, which was decent data. In fact, it's department level and region level in France. So we have hospitalizations, intensive care admissions, as well as deaths for Ile-de-France, which I've picked because it's roughly comparable to London. Its population is about 50% higher, but it's London doesn't give you instances of admission to intensive care. They list daily ventilator bed usage. So this is a cumulative ventilator bed cases, deaths in London, hospitalizations in Sweden. Again, cumulative intensive care. France is the only place so far that we have deaths in Sweden. And those three have very similar, and this whole group has very some place with in Ontario, Canada, where my mother lives. We have, fortunately, she doesn't live in a long summer. So here we go. That's what the hospital admissions look like in Ile-de-France. Well, you can see how good the fit is, and you can take our word for it, you can check for yourself that the accuracy is just as good as what we've seen. Quite high levels of A, 0.09. Okay, these are deaths at a little lower level, 0.08. But again, it's extremely good fits. You can that's not a bug, it's a feature, right? This is London, where again you have even slightly higher admissions in spite of policies.
Yeah, slight.
I don't know how deaths are recorded in France or details of other places. In England, the reporting of deaths has made it very difficult to understand. Because anyone who died within 28 days of a notorious as a COVID-19 death. It's being updated all the time. I think the months. Okay, so these are small numbers, but it's very noticeable if you actually look at the data. You go back and say, wait a minute, that day was 184 before, now it's 192. Right? And sometimes they go down. So you also see negative deaths in lots and lots of data sets. Sweden, half the rate of the other two countries. Okay. Likewise for hospital. So you can see this is a accumulated ICU usage. There's 34,000 people involved, but only 16,000 hospital admissions. So this is day by day. They tell you how many people are in ICU, and I've added those up. What we really want to see is the derivative of this, but it's much better to smooth it by taking the cumulative and differentiate the Gompertz function than it is to do it the other way.
Yeah, a lot of people try to get averages on the data to try to smooth. It's much simpler to take the cumulative and.
Yeah, well, as you know from looking at any of these things, the wild variability in the daily things, and so smoothing by integration is helpful, right? And that's what we're doing. We're not doing anything else to the data. So here you can see some reasonably rough and ready data from the city of Rio. I don't think there are any negative deaths in this list. So we'll come back to this later, but this the peak in this in the velocity, the turning point, the inflection point in this cumulative, in this Gompertz Gompertz function occurred on the 30th of May. So the average gap is about 20 days, according to a statistician who's published a paper about this in biometrics slides. So that means that the peak infections probably occurred about the 10th of May. So, you know, you can always use those dates to go back and see what the governor was doing at that time, or the mayor. Here's Manaus. Again, basically a perfect Gompertz function fit. Peaked earlier. Peak infections probably occurred about there. Here are the long-term care home deaths. Notice that they're about 14. Say 3,000, but Ontario's 1750, 1,800 in long-term care homes. Well, who's in long-term care facilities? Elderly people. When do elderly people normally die? In the flu season in the Northern Hemisphere. So even given that, it's quite extraordinary that the pace of this was so much higher in the long-term care facilities. This is a problem that people have recognized. I mean, it's been the case all over the world in places where it's not family, but the care provider government that provides the care for the elderly. So the errors in these predictions, I mean, I'm not going to show you 100 slides with the errors that they made. They're exactly the same pattern we saw with cholera and Ebola. Right? I'll show you a couple. And this shows you that they're not, the errors decrease, but they don't necessarily decrease monotonically, especially if you just rigidly do a week at a time, because you could pick a bad date. But what happened here when we picked a bad date is the error got above 10%, but it stayed below 20%. Until the end of the epidemic. So these are very small errors. Anybody who's looked at projections with error bars of plus or minus 60 or 70% will realize how different this picture is. So there's London hospital admissions. Again, the first one was only good for a couple of weeks, within 20%. Oh, a bit of, now for a word from our sponsor, mathematics. Here's the Gompertz function again. That n, that number of susceptible people, the final number of deaths, whatever it represents, is a constant, right? It's Gumbel distribution. And the Gumbel distribution is an exceptional distribution. It's not just any old S-curve, as phenomenological modelers are fond of invoking. It's one of the extreme value attractors. It's determined by the location scale group, the affine group on the line. Those two parameters are the initial conditions for a natural differential system. In fact, it's a Hamiltonian system. B is also comes from a symmetry, but it's not a Lagrangian symmetry. There's no Noether's theorem to give you a conservation law from B. But in fact, the differential system is so special that it's equivalent to the structure equations of the affine group itself. Right? So this couldn't be more special as a distribution. And its feature as an attractor, we'll explain later, makes its appearance in epidemic models basically inevitable. So if you think back to what you were doing as this thing was first unfolding, I was certainly looking at the relative rate of change as I saw new numbers every day. the impact, and you want to think about something like herd immunity. What is the impact for the herd? It's the proportion of the herd that's being infected as a relative rate. So in other words, just a logarithmic derivative. Now in the case of exponential growth, that's a constant. Alpha is the exponent. But for Gompertz function growth, this thing decays exponentially, and that's what Levitt was observing, or at least he was observing the logarithm of this behavior back in 2020. So this is a little calculus exercise. Just, in fact, if you want to turn it into a geometry exercise, you do it in the standard Gumbel distribution, and then transform by the affine transformation is 0. There are only 2 critical points for the third derivative. T1 is where the acceleration peaks, and it happens very early on in the process. Of the population infected when the acceleration has reached its maximum. So this growth is rapid, but I mean, you couldn't have anything less like exponential growth than this. The velocity is still increasing. It hits its peak as the acceleration turns negative, and that's at minus b over a. And the value that x takes there is n divided by e, which is approximately 0.368 times n, or 37% of the population infected. Now, the distance between these 2 times is a nice the faster you get between the max. So or the UK. It's its global minimum at T3, which is just S of A to the other side of T2. And there you've hit almost 70% of the population. So again, this is something Levitt used. Because we're counting time in days here, right? And those are very small compared to the scale that we're working on. The first difference is a very good the black is the actual data, red is the derivative, and black is difference, right? So those and the gaps in any of the fitting, right? So what does that tell us? Well, the derivative is decreasing for every time after T2. That means the daily increment is getting smaller and smaller and smaller. This way possible. The average number of people that are later by everybody who's infected today, that number is now less than 1. And that means we see herd immunity in this Gompertz model, which we see has incredibly good agreement with the real susceptible population infected. Now, Portuguese mathematician Gabriela Gomes, with collaborators, came up with the insight last year that if you relax the extreme is that with a much lower level of herd immunity and completely consistent with in the latest version of this with Gompertz function. So what happens after that? Well, the answer is in influenza cycles. And for this answer, we have to thank Gabriela indirectly. I don't think she knew the data was there. When we asked her where to find COVID data on Portugal, we found the source also had influenza data from Portugal. So we have found by looking at that, simply looking at data, always a good idea, that the linear growth as you enter and linear growth as you exit, Gompertz function growth in between every single year. There's Portugal. By the way, looked the same in totally disrupted as influenza cases have everywhere in the world since the advent of COVID-19. So these are the daily cases. These are diagnoses. This is not something like the PCR testing where you have serious questions about the actual presence of an illness as opposed to presence of a virus associated with the illness. A diagnosis has been made here. Somebody had to go to the hospital or go to the health service. So you can imagine that this is actually probably this record. And I already showed you the curve from Alante. Portugal is broken up into EU reporting regions, EU Portugal anyway. This is the Alentejo region. We saw the cases for the whole country. But of course, we've got the granularity to look to see if there's any south. So, right. But you see, again, for Portugal, 2017-18, a perfect fit to a Gompertz function. So here's what happens if you stick them all together the way we've been doing with COVID-19 cases and deaths. And the red are Gompertz function growth. The dark blue is absolutely linear growth, right? And the light blue is the what's not hidden by the other two. That's piecewise linear to an extremely good approximation. Okay, and when I say they're here's how what you see. There's the linear growth. Direction. Well below that line. These lines, the R squared is like 0.9, usually 0.9, exactly a straight line. Endemic disease, right? You have exactly the same number of infections tomorrow as you have today. You have the same number next week as there are this week. The reproduction number is 1. And so the slope rises as the new season approaches. Of these, and you can basically navigate through the whole thing with errors well below 5% by just extrapolating. So here's what it looks like. Again, you can see that the Gompertz function takes off and it's highly nonlinear. That linear growth running into it would be way below the Gompertz level. Wouldn't be more than here. Right? And again, you have agreement. And the same thing happened in COVID-19 after the initial outbreak. So this means we've made the transition to endemic COVID-19. It's already there. Reappearance when you should have expected it, the seasonal peak. So flu season is a misnomer. Viruses, the ones that are responsible for colds, as well as the influenza virus, all follow these cycles. And in Manaus, that cycle peaks in the, it's called winter there, all right, even though it's in January. And here's what happened with COVID-19. Have absolutely a couple of the end of the previous one and the beginning, the end of into the beginning of the next. Change in, you can see the change in the tangent direction at the end of that as well, right? And you can see it again at the end. That's the beginning of the linear behavior. And hospital admission, something that the government has been in an absolute panic about, devastating the health system, actually. They now have between 5 and 12 million on waiting lists for the National Health Service in a country that only has 60 million citizens. So, hospital admissions for COVID-19, this is probably more many others, because this required a diagnosis. So you didn't get into the hospital in London, a scarce resource, as a COVID-19 patient because you had a cough. You had to have a doctor diagnosing a case. So these are probably real cases. But nevertheless, you see exactly the same process as you see in endemic influenza. There's an absolutely linear run up and an absolutely linear exit. And this happens, this ran from December to late March, peaked at a time that makes it absolutely clear that all of the government's subsequent non-pharmaceutical measures were totally, had nothing to do with the fall in the case. So you can see very quickly with these things. And it happened too early to have been caused. So here's the comfort fit. Another one of these ones. It's just, it's ridiculous how well that fits. And you can try this yourself. Andre and Alexei, certainly, you've probably got a Gompertz calculator going already. Right? This is running courtesy of my brother, the numerical analyst, but it's not.
Maple can do it.
You can do it with Maple. I imagine you could do it with Mathematica. God help us, you might even be able to do it in Excel. Python's most of the time it takes, which is zero almost. Being spent drawing the picture. Right. So this is something that can be done on a massive scale. There's incredible amount of improvement one could make. We're using raw data. We don't take out the negative deaths. We leave them there. Right. We don't smooth things which were obviously messed up by periodic gaps like weekends in the reporting. So there are many incredible number of things you could do to improve the convergence. So here we are in Brazil. It's 6 months out of phase with the Northern Hemisphere one. This is the monthly deaths from pneumonia and influenza combined from SUS. And you see these very, very strong peaks. You actually can even see those peaks all causes. It's not necessarily anything to do with pneumonia, but deaths from all causes also peak in Brazil quite strongly every year in June. And I didn't put the slide of that, but we managed to get daily deaths from all cause data from a semi-licit source, if I remember right. And we also got it for Manaus. And there you see the winter, the rainy season peaks as well. So we have this strong cycle here as well. Now, you saw the city of Rio de Janeiro deaths graph. We don't have, unfortunately, we have not been able to get hospitalization data. It must exist. And we would be able to predict it as well as we do the rest. But you saw already the Rio death thing in the first case. It ran till the 7th of August. Then the linear phase came in. I mean, there are two pieces to that linear phase. The one from the 8th of August to the end of December, and the next one from the 1st of January to the end of February. The linear regressions are almost identical with the graph themselves, the actual cumulatives. So there's an English doctor, now deceased, who lived through as a schoolboy, lived through the Spanish flu epidemic, and in fact, and grew up to be a doctor and studied influenza for his entire career for the World Health Organization and in private practice in England. So he produced a treatise which you can find on this website. So it might be out of print, I don't know. But he studied seasonality, right? And he divided his observations up into northern tropical and southern temperate and southern tropical. Well, Rio is basically right in the center, as you guess, of the southern tropical. Right. So on the peaks in June or July. Okay, so where are we with the cycle in Rio? Well, here's what happened after the linear phase stopped, 1st of March. You see this is, there are obvious reporting lags here. This is a more or less a series of steps. Of course, it's going to look a little different if you strip. So the Gompertz function here peaked on the 20th. It was the end of March when the infections peaked, and that fits exactly with the Hope-Simpson. The infection peak fits exactly with Hope-Simpson. So and hope we don't, but it wouldn't be surprising. In fact, in Florida, which is in the three Gompertz function growth phases, separated by linear growth. Exactly. Perfectly with the seasonal pattern in the northern tropical zone that Hope-Simpson found for influenza. So again, the errors are nothing new about these errors. One you see here is this highly oscillatory error. That's not a feature of the fit. That's a feature of the data. Right? Those zigzags in the errors, out of sample errors, are being caused by those steps in the data. But you're very %. Repeating what I already said. So it should be used. It doesn't require a committee of experts to dither and dally about coming to a consensus about what the reproduction number might be, and then whose model is the best one to stick it into, and so on. Anybody can do this. Many of the people listening here could have put their code together by the time. There's masses of data, so it's very easy to check what we've said. So why is it inevitable that you see a Gompertz function? Well, as I observed before, the dynamics is driven by this Gumbel distribution. So this mantra from Cartan, which is the subject of the course that I had intended to be giving last April, and which do, Cartan showed that transformation groups generate geometry, and geometry generates invariance, like curvature. It's a very beautiful world seen through Cartan's techniques. So the Gumbel distribution, as I said, is one of the exceptional distributions. It's given by the group action here is the location scale group on univariate probability distributions. T goes to AT plus B. Okay, this is the absolutely natural group for probability distributions, because it's right, it's not a lot of candidates. The next biggest group before you get to the full diffeomorphism group, T goes to phi of T, is the fractional linear transformations, and they don't like to distinguish between finite and infinite. So if you want to talk about probability distributions, you need to be able to talk about means. Not that all the distributions have one, but so this is the natural group. And of course, this is the reason that you see these location scale parameters in the textbooks. Compartmental models do this sort of thing, as well as the phenomenological ones. If you're describing cases as the susceptible number n times some function of time, the unknown function of time is just the fractional number of cases. That's what it is. Of them. Family of probability distributions. So what does that tell us? Well, the observational data tells us that that density better be asymmetric, and it better have a peak very close to the quantum 368, just like the Gumbel distribution. Otherwise, it's not going to fit all of that data. And you can try, if you want, once you've fired up your Python fitter, put the logistic function in, and you'll see it gives a terrible fit. It's all literature. It underestimates the fit can see the inflection point. Point 0.5 quantile. It comes at symmetric, right? Well, in fact, it comes at the extreme value theorem, which is a beautiful limit theorem that's not as well known as it ought to be, surely. It tells us that asymptotically, every thin-tailed distribution is approximated arbitrarily well by a Gumbel distribution. Now, thin-tailed is just about every distribution you've ever heard of besides the Cauchy distribution and a few other things, right? So anything that is likely to occur in nature describing the playing out of an epidemic is likely to be thin-tailed. And that means you've got the Gumbel distribution by default, asymptotically. Now, the thing is that we, it's again a bit of unfinished work that's meant to be done here and probably will be now. We gave a new proof of the extreme value theorem. It's simply geometry. it shows that the exceptional distributions are characterized by having constant curvature, and the Gumbel distribution is a zero curvature version. Right? And what's more, instead of just saying it's approximated arbitrarily well asymptotically, we can actually measure using invariance how close you are to converged at any quantile. Right? It's simply a matter of how close your invariant is at that quantile to the constant invariant you're heading for. And that shows you that, in fact, asymptotic can be very, very close to the mean. So a consequence of that is find a distribution to fit that model. It have the symmetry, the asymmetry rather, of the Gumbel halfway line. It's going to be very close to a Gumbel distribution anyway. So, you know, what's the point in something else? And why would nature pick something else? Right? What we're describing here is a human immune response. It's developed, and it probably goes way the bacterial immune response. Bacteria respond to viruses with an immune system. And somebody in a lab somewhere produces Gompertz function behavior or not. So, but a practical consequence of this is you get very poor fits if you try to replace the Gumbel distribution by logistic, normal, Laplace, anything else. Right, that's why. So it trying to talk about, where they relax this, as I said, hopelessly assumption they produce model output fits a Gumbel distribution. Line for the inevitability of this. In fact, it's also a way that you could perhaps have of improving the inhomogeneity, because being Gompertz is certainly consistent with, as Gabrielle has now shown, being consistent with a SEIR model. It isn't consistent with a constant coefficient one, but it is consistent with one in which the homogeneity is dropped in favor of realistic model, much more realistic model of the heterogeneity of the population. And so it's consistent. The process, speed it up, make it more accurate, whatever. Anyway, so I've already mentioned that the fits were credited to my brother, the physicist Brad Shadwick at UNL. You can do the same thing with rather more painfully using Maple's nonlinear fit package. And you want to compare with anything we've done. We're numbering days from 0 for the, but it will, of course. As I said before, there's the first reference is a place where we found the links don't all work, but there are links to a lot of data. Some of them are too old, even 2 years later. Some of them are too old to work anymore. But we found a lot of the data that we presented by this paper, links in this paper by Berger. Simon Wood, the Edinburgh statistician, has a paper to appear in Biometrics that the gap between infection peak and which you can find on medRxiv.
Yeah, very naively, we thought that it should have been a depository, a database of
I almost got in a fight with a distinguished scientist at the Institute in Princeton because I thought, okay, he's just going to direct me to where I find all this data, and he thought that I must know that you only find this data by trolling through myriads of articles and chasing down the unusable references that they give, and he thought I was asking him to do that before we understood each other.
But
should be a database. I've discussed this with Marcelo briefly last. It's pain. I mean, every observation we've made here could have been made a year ago, if these data sources had been available. Because you don't start with a conjecture that this thing might work and not check it on everything you can find to see where it could go wrong. And so it took a very long time before we were able to do that. There was as I said, a huge breakthrough when we finally got the influenza data. And by the way, I did, courtesy of a mathematician named David Earn at McMaster, he was kind enough to give us data that they painfully just transcribed for influenza from the registrar's records in England and Wales. And these linear gaps exactly show you how to pick out the three waves of influenza in England.
The Spanish flu.
The Spanish flu epidemic in England. So I should stop here and see if anybody wants to ask any questions before I use up the whole. Oh, I've already used up the whole hour. Sorry.
Okay, well, thank you, Bill. Let me clap maybe here in the name of the audience, because
Thanks.
Most people are muted. Thank you both. And so if anybody has questions, please raise your hands and I'll call up for, or just maybe open your microphone in order to ask Bill and Anna a question. Okay, Artur, please ask a question.
So first of all, Bill, thanks for the talk. As it happens, me and Dan are working on a very similar problem, right? We're working on trying to model COVID in Brazil as well. And I found it kind of, how can I say it? A little bit surprising that logistic distributions didn't work very well when modeling these things, because, well, at least at first glance, it seems like the complex function and the logistic function would be, well, at least up to first order, very good approximations of one another, right? And if you take a Taylor expansion or something, just how bad these logistic approximations were, really.
I wish I had stuck that picture and I forgot to, but I can send me an email and I'll send you some examples. But they really seriously cut below the actual peak. And another thing is that the geometry couldn't be more different. They're only it doesn't have has its own Hamiltonian, and the one that the logistic distribution has is totally different from the Gompertz function, the Gumbel distribution. So geometrically, they're absolutely distinct, except in this limiting attractor. But I'll send, as I say, I'll send you happy to send you actually, Andre, is it possible to post slides or?
Well, I don't know. It's going to be recorded. I just don't know exactly what's the link of the recording.
Yeah, no, it's better to leave it alone. So I can send you examples of that. Yeah.
Perfect. Also, I might end up asking for your data if you don't mind. I mean,
some of it doesn't belong to us, but if I can show you, I can send you the sources for the stuff that we do have. So, I mean, for example, I don't have permission to disclose David Earn's data, for example.
Yeah,
but there's with yes.
Yeah, and just another comment. Working on a very similar problem, we ended up reaching something called a multiplicative calculus, which I'm not sure if any of you are familiar with. I certainly wasn't. But as it turns out, the Gompertz function, it is very much related to something that we call the multiplicative derivative, right? Which is essentially they create a multiplicative analog to the derivative, which is like fundamentally additive in some sort of way, right? And as it turns out, it really does model multiplicative phenomena like the spreading of viruses and so on exceptionally well. So perhaps there is some intuition to be found there outside of probabilistic distributions. As you said, well, the Gompertz function probably is a good fit due to its probabilistic properties and so on. But the natural physical phenomena going on here of things spreading out in a multiplicative manner also points out to these things and stuff.
Yeah, my favorite analog is Galileo's revelation that projectiles followed parabolic paths, right? Another 3-parameter model. Nobody knew why until Newton came along, or nobody could demonstrate why that was. And we have no insight into why anything's happening. But we think that it's overwhelmingly important right now to be able to predict what is going to happen. And you can do that with this approach.
Absolutely. Okay. Thank you very much, Bill. Once again, thanks for the talk.
Thanks.
Okay, so any more questions? Let's see. Okay, somebody raise their hand.
Well, it's me. It's Mike Evans.
Okay.
Hi, Mike.
Canada. How are you
Hi.
doing? I wondered if there's a theory of any inference associated with your fits.
what's the question? Sorry, I missed that.
He wants to know if we know any statistics. We don't.
But you
No,
could,
we should
presumably, right?
Yeah, I'd love to talk about it. We got partway through the lecture you sent to Anna the other day, but we had to stop. Absolutely,
no
be interesting to talk. Let me know when you've got some time, and we'll do a FaceTime call.
Okay, thanks very much. I enjoyed the talk.
Great, thank you. So Mike is an old friend of mine who was an undergraduate friend of mine who became actually by far the smartest guy in our undergraduate class, but he became a statistician.
Smarter than Bill, can you imagine?
Oh, oh, okay. Well, thanks, surprised Mike, for your question. Right. Yeah. So, any more questions? And well, if not, well, thank you again all for coming. Thank you to the couple, Anna and Bill, and please, everybody, stay healthy. And oh, before I just shut down. Alexei, a quick question for you. Everything worked well. I'm recording it.
Oh, you have to stop it.
I have to stop it. But then, where will it be? Where will it go in the universe? Will I get a link?
You will get the email
I will get an email
with a link. Yes.
with a link. Okay, then I'll share it with you, Bill and Anna.
It'll go to Google to be data mined first, right?
Whatever, it will be somewhere in the universe, but okay. So
All
thanks,
right,
Alexei.
that's
So
great.
everybody stays.
And you have to change Andrei, you will have to change the property of this link to be accessible from outside IMPA.
Okay, I'll learn how to do that afterwards,
Please.
or I'll ask you a question. Okay, thank you, everybody, and
Thank
be
you.
safe. Okay, bye-bye.
Great to see you all. Thanks for coming. Bye.
Thank you.
Thank you.